Namaskar and welcome back to this course on infrastructure asset management being offered under the MOOCs scheme, an initiative of the Government of India. Welcome now to the second lecture of this week, where we will be talking about the concepts of deterioration and performance over a period of time. Once again, I would like to remind you that the material used in this course is strictly for academic and instructional use in this course, and it's not expected that you will use it for any other purpose. What you see on the screen is like the blackboard. Please make it a habit to make notes in the good old-fashioned way, what is visually projected and orally stated. To recap what we did last time, we talked about the conduct of the course, we talked about the overview of infrastructure asset management, including the life cycle. We talked about the fact that infrastructure involves massive initial investment and has a very long service life. The components of infrastructure could be in diverse environments and subject to damage over time due to this exposure. We saw several examples of photographs drawn from concrete structures subjected to different environments. Then we talked about the fact that the process of deterioration cannot be lost sight of in a comprehensive approach to infrastructure asset management. Moving forward, our discussion today will be largely focused on discussing the concepts of deterioration and performance and the fine line between them and their interrelationships. Based on our belief that infrastructure asset managers need to know the basics of the processes at work that attack and cause deterioration in order that they are able to formulate and implement a strategy for effective asset management. Based on concrete as a basic material chosen as a case to put the argument forward. So, in the last lecture also and in this lecture as well, we will be talking about concrete structures largely. There are two reasons for it. One is the fact that I am more familiar with the concrete material, and the second, which is very important, in a lot of our infrastructure, concrete is a very important material that is used, and therefore the degradation models, the non-destructive testing methods, all these are discussed in the light of concrete structures. The belief is, or the hope is, that once you understand how to handle concrete structures, you will be able to handle structures made of other elements as well, using the basic framework that we have developed. When we talk of concrete structures, very often we mean reinforced concrete structures. So, the picture here shows the construction of reinforced concrete, and this part here, all these steel bars are what is called reinforcement, and you can see that concrete is being poured and vibrated using vibrators to ensure compaction. In the fresh state, concrete is plastic and can take the shape of the formwork, and therefore we have this formwork here, which will be later removed after the construction has been completed and the concrete has hardened and has taken a shape of its own. In fact, it will take the shape of the formwork. This discussion is more for those who are completely uninitiated in the idea of reinforced concrete. A very important component of this construction here is this concept of cover. Now, if you will notice, above this layer of reinforcement, the top reinforcement and the bottom reinforcement, below the bottom reinforcement and above the top reinforcement, the concrete is placed like this, which in section looks something like this, that you have reinforcing bars here and the concrete is here. In the bottom, the reinforcing bars are here and the concrete has been placed here. So, this thickness here is called the cover thickness. So, when we are talking of deterioration of concrete structures, we talk about two things in principle. One is the deterioration of concrete as a construction material, and the fact that if the concrete is compromised, then the steel also would be exposed to environmental action. We have to be careful that in our design processes, in our maintenance efforts, we keep track of what is the state of integrity or what is the state of deterioration in concrete as well as in steel. This picture here shows how the cover thickness is prescribed to be varying depending on the aggressiveness of the environment. Since this is a course not really going into concrete technology and concrete engineering, design of concrete structures, we will probably not go too deep into it. Suffice for you to understand that this cover concrete, which we talked about here, this serves two purposes. One, there is a structural function, and the second is a protection function. The protection function is protecting the reinforcing bars from environmental action directly. So, naturally, if the aggressiveness of the environment, whichever way we define aggressiveness, if the aggressiveness increases, the prescribed cover thickness to this steel bar is supposed to increase, is provided for in a manner that it increases. For weak aggressiveness, it could be as little as 25, for moderate it could be 30, for strong it could be 50, for very strong it could be 55, or whatever the numbers are for different codes. Different countries, different professional bodies prescribe their own codes, their own specifications for construction of concrete structures, and they have their own way of classifying the environment in terms of aggressiveness and classifying or laying down the cover thickness. With this very simple primer to concrete and reinforced concrete, trying to look at an illustrative example to bring out the concept of deterioration and performance in a slightly interesting light. Now, let us think that wearing glasses to correct vision shows some deterioration in the functioning of the eyes. We are normally supposed to be able to work in an environment or work in a manner that correction in the power of the eye is not required through glasses. However, for whatever reason, it could be age, it could be genetic, it could be high screen time, or whatever the doctors may say, there is a situation, quite often I should say, that people need to have glasses, and with glasses the vision is corrected. Now, the issue is what has happened? There is some deterioration in the functioning of the eye. The question is, does wearing glasses affect the performance of the person wearing the glasses? The answer could be yes or no, depending on the job requirement. Now, if the job requirement is such that it is expected or it is likely that wearing glasses could be an impediment, in that case, the question would be, can the person wear contact lenses? Those are matters of detail which we do not want to go into it, because it is at the end of it, it is an illustrative example and we are trying to make a point. So, the basic point is that performance is not directly related to deterioration. The performance of a person wearing glasses is pretty much all right as far as his ability or her ability to read is concerned. There is no other compromise that happens except that you are wearing glasses. Now, the question I have for you is to find out, how do employers lay down the requirements for employment? Is it in terms of performance, that well, a person should be able to read from a certain distance, do certain things at a certain distance or a certain way and so on? Or is it in terms of the power of the lenses being used, if that is the case, for someone wearing corrective glasses? it could be done both ways, and my request to you would be to find out how is it done by one employer, another employer, and so on and so forth. Moving forward, there is another question for you. Let's consider that as traffic grew over time, the time taken to cross a bridge becomes unacceptably large. You make a bridge over a river, a flyover, or whatever you did, assuming that you will be able to go over a bottleneck, cross the river in a certain period of time. Now, as the traffic increases over time, the time taken to cross the bridge or the flyover keeps on increasing. If you reach a stage where the time is unacceptably high, now in that case, how will you answer these two questions? Has the performance of the bridge changed? Has the bridge deteriorated? The way I would look at it is that nothing has happened to the bridge. The bridge remains whatever it was, in whichever shape it was, except that the performance of the bridge has changed because the traffic has become too large. The question would be, did we foresee the kind of increment or the kind of increase in the traffic that we actually saw? In other words, did we foresee that the time that it takes to cross the bridge would increase to a certain level within a certain period of time or not? So, these two examples, one of the eyesight and the other of the bridge, hopefully make the point to you that deterioration and performance are not really the same thing. There is a relationship between them, but there is a fine line between them as well. That if we look at a structural system, whether it's a bridge or a beam or a column or whatever it is, under the action of some input, that is, it could be in terms of load, it could be in terms of heat, it could be in terms of whatever other parameter that you choose. There will be an output which could have several parameters, it could be 1, 2, 3, whatever it is. And in this case, the output is related to the input and the system characteristics. So, the system characteristics and the input both will determine the output. Now, in this light, if we look at deterioration and performance, like I said before, deterioration and performance could surely be related, but they are distinct. Deterioration affects the system properties and therefore measured in terms of deterioration parameters. We talked about the eyesight, and there are methods, there are parameters by which the doctors measure the amount of or the extent of deterioration that has taken place, for which a certain correction needs to be made. But that is on the deterioration side, which has affected the system. Obviously, if the system characteristics change, even for the same input, the outputs will also be different. Moving forward, performance is related to the output and should therefore be measured in terms of performance parameters. The point that I am trying to make here is that there are deterioration parameters and there are performance parameters. They should not be confused to be the same. In fact, I have an interesting question for you. Just think about what is the difference between analysis and design. These two words are very often used in all branches of engineering. We do analysis and we do design. Usually, analysis precedes design. What is the basic difference between the two? We will probably begin the next lecture addressing this question and move forward. And I give you some time to think about it and come to your own conclusion or your own formulation. Now, moving forward as far as deterioration, performance and that kind of discussion is concerned, the graph on the left shows an intuitive representation of how deterioration changes with time. It is intuitively clear that deterioration increases over a period of time. Now, whether it follows this curve or another curve is a matter of detail, and we are not going into it. As far as this particular curve is concerned, it is characterized by an initial level of deterioration which is shown here. That is, at time t is equal to 0, this is the level of deterioration which we are already starting with. This initial deterioration can also be looked upon in terms of the defects which will creep in during construction. In an engineering sense, it is virtually impossible to think of a situation where the construction will be defect free. Now, depending on the rigor that we have applied to quality control and so on, there will be some level of initial defects, and that is what is being reflected in this initial deterioration, that is the deterioration at time t is equal to 0. Any point on the curve like this one shown here or this one shown here represents the instantaneous rate of deterioration. That is, if you look at this graph, the rate of deterioration here is very slow, the slope is more or less horizontal, there is no change, and it becomes more prominent over a period of time. There are certain mechanisms where this graph may taper off and there is a limiting level of deterioration. So, those are matters of detail, but at this conceptual level, what we must understand is that deterioration follows a certain mathematical form which is represented here, and deterioration varies with time, there is an initial deterioration involved and there is a rate of deterioration involved. The question to you is, what is the idea of this initial deterioration? What do we mean when we say that even before anything happens, the structure is put into use, there could be some initial deterioration? I am leaving it to you to think about it for a while, and we will address this question when we are talking about inspections and maintenance and so on at a later point in this course. Similarly, if we want to draw the variation of performance with time, performance decreases or degrades over a period of time. Like the deterioration curve, this curve is also characterized by an initial level of performance, and the point on this curve represents the rate of degradation in performance at that point in time. Look at different points in time, there will be different rates of degradation in performance. If we come towards this part here, the rates of change of performance is pretty high. That is, at later points in the life of the structure, when you would recall that the deterioration levels are also very high. Now, some of you will notice that in this diagram, as against the previous one that I used, the initial level of deterioration has been taken to be 0. But this does not materially alter the discussion that we are having as far as the changes in deterioration levels or performance levels over a period of time. Now, if we combine these two, what we get is something like this. Over a period of time, deterioration increases and performance degrades. That said, the question will be, can we look at the concept of service life in this framework? Now, service life is the useful life of the structure or an infrastructure. You will notice that I am using the word structure and infrastructure interchangeably at times, but I am sure you are able to follow what the argument is. So, with these graphs where we talk of deterioration increasing over time, performance degrading over time, how do we talk in terms of, or how do we incorporate the concept of service life? As far as infrastructure is concerned, we talked earlier that the service life or the life in which we expect the structure to be useful is very long. It could be 50 years, 70 years, 100 years, maybe sometimes more. Those of you who are working in this domain of design, the challenge is to you, or the question is to you, that how does the present thought process in design incorporate the kind of discussion that we are having today. When we say that please design a structure so that it will survive for 100 years, and the earthquake loads have to be considered, how do we go about doing it? Does that thought process align with the kind of thought process being talked about here? We will probably try to answer this question at a later point in time, but for the time being, it's an open question which possibly those of you who are working with design should be able to answer, or at least have an understanding of what's being talked about. Now, in order to develop a rational procedure for asset management, we need to define a critical level of performance below which the performance cannot be allowed to fall during the service life of the structure. This is the crux of our thought process. We talked about this graph, which is performance as a function of time. We know that it's going to degrade. The idea is that there should be a critical level of performance. Recall our discussion with respect to that bridge where we talked about unacceptably high times to cross the bridge. If that problem is looked at in this framework, maybe at time t is equal to 0, the time taken to cross the bridge was 2 minutes. At 10 years, it grew to 10 minutes. At 20 years, it became 20 minutes. Now, at 50 years, if it becomes 2 hours, then we say that, well, this is getting out of hand. So, there has to be some critical level where we say that, okay, as far as the time taken to cross the bridge is concerned, my critical level is 25 minutes, after which the bridge will be deemed to be not meeting my requirements. What is shown here in this diagram is that if this was the critical performance level and this was the performance versus time graph, then the service life will be this. The issue is that this is something which we will know only much later. When we design, we fix a service life and then let the game begin. So, suppose we had taken the service life which was here. So, let us consider this to be case 1. If I had taken my service life to be these number of years and the critical level was here and the performance curve was here, then we are doing very nice, because the expected performance at the end of service life is clearly above the critical performance level that we have fixed. However, if we had fixed our service life to be somewhere here, which is what we are calling case 2, then the level of performance at that point is below the critical level, and that is unacceptable. For that, what do we need to do? We need to somehow do something with this performance time graph. Think about it as to what we can do. Please remember that these values for critical performance level or the service life can change with time. You build a bridge and you decide that you cannot just let the bridge be decommissioned, and you would like to continue to use that bridge for another 20 years. Then you will encounter problems like this. And in any case, these are only conceptual models. The reality could be very different. We may assume that the performance curve will be something like this, but it may turn out that the performance curve is something like this, in which case all your calculations will go for a toss. and you need to do mid-course correction much sooner than you expected. And that is what is the whole crux of infrastructure asset management, where you may need to intervene at different points in time and keep track of what is happening to the infrastructure performance. Is it heading the right way? Is it not heading the right way? What is the kind of corrective action to be taken? And so on and so forth. So that really is the crux of our discussion in this course altogether. Having done this detailed discussion on service life using the performance curve, I am leaving it to you as an home assignment to do this discussion using the deterioration versus time graphs. You would recall that we had done this discussion that deterioration increases over time, performance goes down over time. So, we used this formulation for our discussion now, and using this formulation, please try to understand or create a system wherein the concepts of service life and a critical level of deterioration can be appropriately defined. In fact, that is how you will come up with deterioration parameters, and in this case, when we talk of critical performance levels, here we talk in terms of the critical performance levels or the performance level itself to be measured in terms of time taken to cross the bridge. So, this was my performance parameter. So, the performance parameter that we use, in this case we will use deterioration parameters. So, remember that depending on the infrastructure or depending on the actual structure that we are talking about, different parameters will need to be identified and used to be able to follow or monitor the changes in those parameters over a period of time. Now, a quantitative discussion on the basis of these qualitative schematic representations requires tools and mathematical models for estimating initial levels of performance and deterioration, which is what I had shown here. Initial level of deterioration, in this graph I have not shown it, but there was a point where we had shown some level of deterioration initially, and similarly the initial level of performance and the rates of change in performance and deterioration, that is the slopes of these lines at different points. This obviously is required for each deterioration mechanism, the local environment and the system characteristics and how they may change over time. So, once we come to this part, then we need to understand what is the kind of environments in which our infrastructure systems are. And taking a cue from that, let us try to look at some special environments for concrete structures. Here we have concrete structures in water and marine environment. So, this concrete structure or this concrete structure or this concrete structure is in water or marine environment. What is the difference between water and marine environment? Marine environment is basically water with certain characteristics. Bridges in rivers, maybe lakes and so on, there the characteristics of water in contact with the concrete would be different compared to the characteristics of water which is in contact with our concrete structures in the case of marine environments. Another characteristic of water and marine water environments is that the level up to which the structure is submerged is not necessarily fixed. It may vary with the day, there are tides involved, and it may vary with the season. For example, in rivers it definitely varies with seasons. In the case of the sea, it varies with the tides. In the case of marine environment, there is also a splash, which means that a region just above the submerged region somewhere here is subjected to cyclic wetting and drying because of the action of waves and splash. Moving forward, there are concrete structures which are buried, for example, pipelines. Here is an example, the third picture, which shows a deteriorated pipeline because the concrete that was carrying the sewer has deteriorated. As far as models are concerned, the issues involved are what is the kind of characteristics of the fluid that is being carried in the pipe, and what is the characteristics of the soil and groundwater if it is involved around the pipe, and the pipe thickness is whatever it is. This here is the pipe thickness. So, it is a thin pipe, relatively thin pipe, which is subjected to different environments on the inside and outside, and how the characteristics of that environment impact the concrete. So, basically what we are trying to study, or what we need to study, is the effect of these different environments on the characteristics of the concrete over a period of time. In case reinforcement is involved, then we have to keep in mind that whether or not, if or not, the reinforcement will get compromised over the service life of the structure. Then we have tunnels, where we have this kind of a lining. Now, as far as the lining is concerned, whatever the thickness of this lining is, there is some environment inside the tunnel, here or here, and then there is rock, soil mass, whatever is outside, and there again this concrete is exposed to the environment here, which could be in terms of water having certain characteristics, and the kind of environment here, which possibly will not have too much water, but will have certain gases, which may be different in concentration from the atmosphere, depending on what the tunnels are actually carrying. So, all these aspects need to be borne in mind when we are trying to design these tunnels and finally maintain them, manage them over their service life of 50, 70, 100 years, whatever it is. Then we have concrete structures subjected to freezing and thawing. For the uninitiated, I would like to inform you that concrete is porous. Now, it is not porous in the manner that a sponge is. You do not have a lot of water going in and coming out of concrete, but there are pores in concrete, and concrete does absorb a certain amount of water. Some amount of water is also expelled depending on the environmental conditions and so on. Now, when it comes to an environment where there is cyclic freezing and thawing, that is, the temperature of the atmosphere crosses the 0 degrees, which is the freezing point of water, up and down several times in a year, which can be expected in cold regions, then the water within the concrete will freeze and it will thaw. Now, we know that water, when it freezes, expands, and this cyclic phenomenon of the water within the concrete freezing and thawing leads to destruction in the pore structure, and therefore, we have a situation like the one that is shown here, that the concrete becomes highly damaged unless we take certain measures upfront to ensure that the concrete remains durable, or we are aware that if these things start to happen, then can we do something. With concrete structures, it is very difficult to do anything after the structure has been built. There are techniques of rehabilitation and repair which we will talk about, but the principle is that it is very difficult to do something with an existing structure. We may be able to add something to it, but to the original structure, it is something very difficult. We will probably talk about it when we talk about the actual repair and rehabilitation methods. Another example of concrete structures is those which are exposed to sulfates. Now, I am leaving it to you to think and explore as to what are the environments where we expect or we have sulfates which will attack the concrete. There is a situation here which I showed you in the previous class as well, where we have cracking and aggregate pop out in concrete on account of alkali aggregate reaction kind of problems. This is not an environmental related problem. It is not a problem which is arising out of the environment, except for the fact that yes, alkali aggregate reaction will probably not happen very rapidly if the atmosphere was completely dry and so on, but it is a problem that arises because of the wrong choice of aggregates or cement at the time of construction. So, that has its own long term implications in terms of the deterioration. Moving forward, the rate of deterioration is essentially determined by two things. One is the severity of the environmental conditions, and two, the internal ability of the concrete to resist deterioration. I hope that is very clear, that the internal ability to resist deterioration is something what we impart to the concrete by choosing the right materials, by choosing the right kind of construction methods and so on and so forth. Now, if the ability of the concrete to resist deterioration is high, that is, in a manner of speaking, we are talking of very good quality construction, then for a given severity of the environment, this concrete will perform better than another one where the quality of construction is not so good. On the other hand, the same concrete or any concrete for that matter, if it is subjected to environments of varying severity, severity has to be defined. For example, in the case of freezing and thawing, we can talk in terms of the number of cycles that a concrete structure faces in a month or in a particular winter in one place versus another. There are cold regions and there are very cold regions. In cold regions, maybe we expect the cyclic freezing and thawing to happen maybe 100 cycles in a year or 200 cycles in a year. In certain other cases, it may be 50 cycles in a year. So, the severity of the environmental conditions, if it varies for the same quality of construction, the kind of deterioration that will happen will be different. And that is what is meant by what is stated here, that the rate of deterioration is essentially determined by the severity of the environmental conditions and the internal ability of the concrete to resist the deterioration. And therefore, while designing, engineers try to work with models of the environment where the structure is located. They try to understand the characteristics of the environment to the extent that they can. Then they impart enough internal strength to the concrete to withstand the environmental forces. Now, this is strength that we are talking about is different or may be different from the simple concept of compressive strength that we talk about for normal concrete design. So, let me clarify this matter of environmental classification and internal strength through this example. So, here is an example where it is given that in the case of an RC structure in marine environment, the following two conditions should be satisfied at the same time. Now, this particular example deals with marine environment, and that is what we are talking about when we are talking of classification of environments. There can be similar examples or similar specifications given for other environments where the reinforced concrete structure is located. That could be in freezing and thawing conditions, that could be in extremely dry conditions, that could be underground and so on and so forth. So, now coming to marine structures or marine environment, let us look at the two conditions which need to be satisfied. So, the first thing that we need to see here is that this set of specifications further subclassifies the marine environment into these three parts: the submerged zone, the atmospheric zone and the splash zone. Now, what does that mean? That a marine structure which is modeled, let us say, as a simple column or just a member, there will be a zone which is always submerged in seawater. There will be a zone which is all the time exposed to the atmosphere, that is, there is no direct contact with the seawater, and there is this zone which could be subjected to cyclic wetting and drying on account of splash, on account of tides and so on and so forth. So, this specification further subclassifies the marine environment and talks about specifications given here and here for different subclassified areas. So, what we are talking about is the maximum water cement ratio, that is what we are talking about in the first part is the maximum permissible water cement ratio, that is the quality of concrete, its durability, its pore structure and so on and so forth. And it stated that for general construction or for concrete products, the water cement ratio should not exceed the numbers given here, 50% for submerged zone, 45% for the splash zone and 45 here and 50 here for the atmospheric zone. So, the water cement ratio really talks of only the concrete quality and nothing else, whereas this part here, that is the minimum cover thickness, talks about how much cover is there to the reinforcing bar. So, if we have a schematic representation of a marine structure or RC structure in marine environment, something like this, this is the reinforcement, this is the cover thickness that we are talking about, and this cover thickness should be a certain minimum depending on whether this member is a slab or a beam or a column. And there we are talking about different zones, submerged zone, atmospheric zone, splash zone, much like as we did here. And in these conditions, for these different structural members, what should be the minimum cover thickness. So, this is specification for concrete and this is specification for the cover together basically give you the kind of protection that we are affording to this reinforcing bar as far as the chloride action from the outside is concerned. So, that is what we are talking about when we say that a designer tries to impart enough resistance or enough strength, enough power to the concrete, not only the concrete, but the concrete structure per se, which includes the cover thickness, depending on the kind of classification of the environment that has been done. So, this discussion here summarizes one possibility of what can be stated in a specification for marine structures. Now, it is important to understand that different codes will give different numbers. For example, this is a situation for a given code. Somebody else can say, no, instead of 50, we are willing to accept 52, or we are willing to go up to only 40 here, and so on and so forth. So, these codes are different for different countries and these numbers can be different. The second part is that these codes are periodically revised. As we develop more and more understanding of the subject matter, we try to revise our codes. At a certain point in time, we may say that okay, 4 centimeters or 40 millimeters of cover is sufficient. At some other point in time, we can say no, this 40 needs to be revised to 50, or this 50 here can be made 40. It can go either way. So, now we have to understand that different codes for different countries give different numbers and each country is free to revise its code at any point in time. So, now this idea that different codes give different numbers and more importantly or more interestingly the codes are periodically revised leads to a very interesting situation, that a structure which was designed at this point in time with some set of numbers and it is all right, this structure is in service. These numbers get revised. Now, as far as this particular example is concerned or this particular illustrative numbers are concerned, this structure has become non-compliant. It was 40 mm and now it has become 50 mm. You just cannot add 10 mm of cover. In this case, of course, since the cover has been reduced, we do not have to bother about it. The question that arises is that as we revise these codes, these structures could become non-compliant with a particular code at a particular point in time, given especially that these structures have a long service life. If a structure was designed with these kind of conditions, is it the structure's fault or is it the structural designer's fault who designed it at this point that the structure has become non-compliant here? No. But an asset manager at this point in time, we should know that out of the total inventory of assets that we have, how many assets were created with this set of specifications and how many were created with this set of specifications. This is something which is important from the point of view of fund allocation, budgetary provisions and so on and so forth. Now, as a homework, I am leaving it to you to collect and compare information from different codes and provisions therein on special conditions. Now, these special conditions basically refer to different environments. Try to see how does the Indian code or the Japanese code or the Singaporean code or the European code classify the environment. What are the specifications of concrete or cover or stress in steel or crack width and how they have changed with time. You may not be able to get all the information, but I hope that insight will help you understand the kind of discussion that we are doing here. To summarize, deterioration in concrete structures is related to two things. Each of the environments needs to be appropriately characterized. That is, the environments in which the concrete structure is needs to be appropriately characterized. Normal atmosphere, for example, can be characterized in terms of the amount of rain, the temperature variation. If it is a marine environment, we already talked about how we can do it. If it is a freezing thawing environment, we have already talked about what can be done. If it is sulphate attack, we again should be able to say that okay, what is the kind of severity involved and so on. And also the relevant properties of the concrete need to be modeled. We need to understand how does the concrete interact with the atmosphere. At the end of it, what is going to happen? We talked about briefly that concrete is a porous material. Now, if it is a porous material, obviously from the environment, gases like carbon dioxide, oxygen will permeate through the pore spaces and go inside. Similarly, water, seawater, any liquid will also be able to go inside the concrete. The ions outside will be able to penetrate into the concrete. Now, how much of the ions is present, what is the concentration of those ions is an issue with characterization of the environment. Whether they will move into the concrete, the rate at which they will move into the concrete is an issue of modeling the concrete properties. When we do both of these, then we will be able to develop models for deterioration. It is not important for asset managers to be masters of these deterioration models, but the underlying thread as far as this course is concerned is that if they understand that yes, these are the issues involved, they will be able to develop a better, more robust and a more rational strategy for maintenance of structures. Over the years, the following have been identified as major mechanisms that cause deterioration in concrete structures: chloride-induced reinforcement corrosion, carbonation-induced reinforcement corrosion, alkali aggregate reaction, cyclic exposure to freezing and thawing, and chemical attack. There are others, but these are the main mechanisms. We will not discuss any of these mechanisms in great detail, but we will surely touch upon some of them in a later module to give asset managers a feel as to what is the kind of technical issues involved in choosing the concrete and in monitoring its behavior and its properties over time. And with this, we close the discussion today, and we will continue our discussion in the next class, when we will try to look at the maintenance of structures in the framework that we talked about today. And before we close, I will share with you a list of references or material for further reading, which will help you understand the subject matter covered today and being covered in this entire course. Once again, I would like to express my sincere thanks and gratitude to all the teachers, colleagues and students over the last several decades who have contributed directly and indirectly to my understanding of infrastructure creation and maintenance, and some of the slides included in this presentation include their input in different ways, and I am indebted for all their help in the matter. Thank you.